So let me share the screen. So we were discussing the reverse recovery phenomena for power diode and what kind of problem you can have due to this recovery time, especially due to this DIDT. Okay, and how we can avoid this kind of DIDT over voltage by using a Snava circuit. So up to this we discussed in the last class. If you have any doubt, you can ask on this. Okay, so if you don't have any problem, then I will ask you, some of you, randomly, as I told you. Shreyas Khatri, are you there? Shreyas,
Yes, sir.
can you define the reverse recovery time?
Just give me a minute. Hmm. So when the reverse voltage is applied for on a diode, then for a brief period, the diode current becomes negative. So the time from which the diode current becomes negative to the time it becomes positive again, that time is called the reverse recovery current. Reverse recovery time.
Once again, you just repeat. Which time?
Sir, when you apply a reverse voltage to a diode, then for a brief period the diode current becomes negative. So the time from which that current becomes negative to when it becomes zero again, that time is called the reverse recovery current time.
Okay, it's not exactly, but little bit it's okay. Uh, Actually, what happens at the instant where we apply the reverse voltage, the diode current changes like this, and then
Yes.
it recovers like this. Okay, and this portion is not exactly linear, this is exponential. Okay, so that is the problem. So therefore, generally, how you define this reverse recovery time is that if this is the that maximum current in the negative, which is also called the IRR, reverse recovery current, and when the current reaches the 1/4 of this, so that means, so this is 1/4 of IRR. So that time is taken, and this is how we define the reverse recovery time, not zero, because for exponential curve it takes very long time to become zero. So generally we define this time as reverse recovery time, which is again is the summation of two, as I mentioned in the last class, that is T1 and this is T2. Is that clear? So this is the diode current and this time.
Yes, sir. Sir, capital IRR is the maximum reverse recovery current, right?
Yes,
Means the lowest value it goes. Okay.
yes. Now let me ask somebody else. Ishani Chatterjee, Oishani Chatterjee. Oishani, are you there?
Yes, sir.
Okay, so can you tell me in this graph or in this curve of ID, at which point the device become reverse biased? At which time instant?
At the point the current starts decreasing.
Now your answer is this point.
So at the point the
This is reverse bias condition.
yes, sir.
Okay.
Yes, sir.
No, not the correct answer. Let me ask Konishko Boshak.
Yes, sir. Yes, sir.
Can you tell me at which instant the device becomes reverse biased? Actually reverse biased.
Sir, after the ID becomes negative.
Why?
The line drops below the so because the current flows in the opposite direction, which tries to flushes out the
No, in the last class also
minority charge carriers.
in the last class also I mentioned that the reverse this reverse bias is a device phenomena. It's not the external DC thing you are applying. It's a reverse. It's a device phenomena. That means when the space charge region will recover, at that time
Yes,
it will be reverse biased.
yes.
Okay.
When the ID starts decreasing,
Anybody else try to answer this correctly?
So when the ID starts decreasing, that is the when it starts decreasing from the constant value.
That means you are saying the same, no? This point. You are saying this point.
Sir, I can't see the scars. Yes, yes, yes.
Can you see the
That is
code
where the
whiteboard?
yes, yes, yes. That is where we apply the reverse voltage.
No, that is the not the reverse bias condition for the device.
That is where we apply the reverse voltage.
No, I am asking that what is the reverse bias condition of the device? At which point the device actually becomes reverse biased? Anybody else?
স্যার আমি কনিষ্ক বলছি স্যার আরেকবার বলতে পারি যে আফটার দ্য পয়েন্ট IRR crosses and the current starts increasing again.
Why?
Hello.
Why you are saying this point?
Sir,
You are saying this point?
yes sir, because yes sir, after that point it becomes reverse biased completely.
Why?
Sir, because এই নেগেটিভ আইডিটা মাইনরিটি চার্জ ক্যারিয়ার্সটাকে মানে পুরো কারেন্টটাকে স্টপ করে দিয়ে তারপর থেকে মানে ফর রিভার্সে একটা কারেন্ট দেবে।
So you are correct, but explanation is not correct. Not exactly the same. Anybody will try this?
So at the point due to breakdown, the current will increase exponentially. After the IRR is reached, after that point.
That also he has mentioned, but the explanation I need. Oh, can you explain this? Okay, so this is completely due to this formation of the space charge region. Actually, that in the T1 time, the excess carrier that's stored in the drift region is removed. Okay, so you can say that T1 is the time for removal of the excess charge stored in the drift region or this N minus region. Okay, so then only it becomes reverse bias. Otherwise, it cannot be a reverse bias because if there is some excess charge carrier in the present in the this drift region, so it cannot be reverse bias. Okay, so in the reverse bias condition, there should not be any excess carrier. Once the excess carrier is removed from this space charge region or drift region, then the device becomes reverse bias. So it takes that time, that T1 time, to remove all this excess carrier which is stored in that drift region or the space charge region. Okay, is it clear? Any doubt? Okay.
Sir, can you explain it once again?
Now, once there is some excess carrier in the drift region means for this case the N minus region. If there is some excess carrier present, then the device still in reverse bias, this forward bias mode. Once all the excess carriers are removed from this drift region, then the device becomes the reverse biased. Okay, so it takes that time, that T1 time, after it crosses 0, it takes T1 time more to be free from this excess charge in that drift region. Okay. Now it's completely device phenomena, and there is a you can say there is some distribution pattern change inside the device. The distribution patterns are different in at different point. If we go linearly from this positive to negative terminal of the device, uh, then we will say we will see some a peculiar pattern which varies with respect to time. Okay, so if we uh, go like this linearly, if we let's draw this, if we go linearly, then suppose these are the two junctions. So this you can say P plus and N minus, and this is N minus and N plus junction. Okay, so then that when the device is carrying the current, so that time the distribution is like this. All the distributions are exponential. So this is the distribution. This is the minority carrier distribution. Then once we switched off, then the distribution becomes the changes like this with respect to time, like this, then like this, and like this, and like this. So this is how the distribution changes. So this is the change in distribution with respect to time. So after that, there is no, yeah, this actually you see, this is the concentration of the density which is found in this N minus region, which is at the end of this reverse recovery, that almost 0. Okay, and finally it gives this pattern. So if we see in that off region, so it forms this type of concentration. Minority carrier concentration is like this. Okay, again if we switch on the device, again there is some build up phenomena. So that is different from the switch off phenomenon. Okay. So that is the thing. So it's you just remember that reverse bias is not the thing we are applying from the external device, external power supply. The reverse bias or the forward bias is biasing is completely the device phenomena. So if there are excess carriers in the drift region, then it is forward bias. Otherwise, if it is a depletion, it is depleted one, then it is called the reverse bias. Okay. Now from this we can understand one thing, that in a power diode or any diode, so some time is required to uh, to get the thing back. Now this time actually you can say some here is some like a capacitor. Uh, Suppose in a capacitor, if we have a capacitor, okay. Now if we apply some charge, so it takes some time to store the charge in the capacitor, to make the capacitor full of charge. So here also there is a storage time for this diode. So we can say a parasitic capacitance present in the diode. So we can assume a capacitor present in the diode, which is a is a hypothetical case, hypothetical thing, that this parasitic capacitor which comes across the diode. Okay, and we can think of this capacitor, and due to that capacitors, that the time for switch on and switch off, it is not instantaneous. So it takes some time to switch on fully, and it takes some time to switch off. Okay. Now, due to this capacitor, the time varies. Actually, for there are different types of recovery for diodes, that also I mentioned in the last class. That fast recovery diode, or that hard recovery diode, and that soft recovery diode. Okay, and the soft recovery diode and the DID, that I think I mentioned in the last class, that for DIDT, for the soft recovery diode or SRD, is less than the DIDT of hard recovery diode. Hard recovery diode means which very fast it recovers. That means this type of thing. So it recovers very fast. This time is very fast. And the soft recovery means it's a very slow recovery. Okay, so that means it depends on the device itself, that at what rate it recovers. Okay, now if we think of this very fast recovery, then there is another option which is called the Schottky diode. Have you heard of this Schottky diode? Anybody? Schottky diode, have you heard of this?
No, sir, no.
You haven't heard. Okay.
The majority carrier device.
Huh? Follow?
That is a majority carrier device.
It's a majority carrier device, but what is the how it is formed? That means what is the components inside it? What are the components? Is it a PN junction diode? So it's not a PN junction diode. So in normal diode, what we have some P substrate, we have some N substrate. Okay, so like this, and the symbols are generally we draw like this. But here we have a metal connected with the N substrate. What type of metal? The metal can be chromium, can be platinum, can be molybdenum, like this. Can be chromium, can be platinum. Okay, so there are some materials which can be used with this N type of substrate to form the Schottky diode, and the symbol also is a little different from. Okay, so this is PN junction, and this is the Schottky diode. C, more C is there.
আরেকবার বলবেন?
হ্যাঁ বলো কি বলবো, কোন জায়গাটা বলতে চাইছো বলো। So there are two types of device I am discussing now. So one I have already discussed, that is the PN junction, where you have different substrate. One is P, another is N. Okay, but in case of Schottky diode, we have only one semiconductor substrate, that is N, which is connected with a metal. Okay, so it's a thin film of metal which is placed on the N type of substrate. And what type of metal we use? We use chromium, platinum, molybdenum, etc. So why this type of metals are used? There is some specific reason for that. That is, this type of metal has low absolute potential energies. So you can write down the term. So this type of metal has low absolute potential energy. Okay, so this is how it is formed, and then what happened there? A depletion region also formed there. Now, if I draw like this, the actual vertical structure. So this is the anode, which is the metal. Okay, so you can say this platinum, and you have this for this power application. We can use two different substrate, and this is the cathode. Okay, is it okay? Now there is some depletion region is formed in this. Why this depletion region is formed? Because as it has a low absolute potential energy, the electrons from the N substrate go into the metal. Okay.
Sir, your audio is having problem.
Huh?
Sir, your voice is breaking, sir.
My voice is breaking. Is it?
Yes, sir, getting distorted.
Maybe due to the internet issue. I don't know. Is it coming clear now? Is it coming clear?
Yes, sir, it's coming.
Okay, so that means when we connect or when we place this metal on this that N type of substrate, what happens? The electrons in the semiconductor or N type semiconductor material, N type semiconductor substrate has a little bit higher higher absolute potential energy with respect to the metal. So therefore, the electrons from this N-type substrate go into the metal, and as a consequence, the metal becomes negatively charged. Okay, so when the electron flows there, so what will be the result? The metal which was initially was uncharged, now it will be negatively charged. Okay, so if there is a less electron here, then the depletion region will be formed inside the or at the boundary of the two things. That means the N and this metal, N-type substrate and this metal. Okay, so you can say that as this majority carrier, because here the electron is only the majority carrier. So as this majority carrier goes into this metal, so it's basically a majority carrier device. And in case of PN junction diode, we have seen that both the polarities are created. That is the plus and minus, positive and negative. Both the polarities are created in this space charge region. But in case of this Schottky diode, only this negative charge is created. So therefore, it is also called the unipolar device. It's not a bipolar device. So that is the difference between the PN junction and the Schottky diode. But the major difference which we'll discuss here is the reverse recovery time. The reverse recovery time is very less or the least for this Schottky diode, because you have seen uh, here we haven't used any external uh, say, or there is no stored charge phenomenon. Okay, so as we have seen that in case of diode there is a charge storing phenomena, charge storing time is required. So here you don't have to okay, again the connectivity issue appears. Okay, so here the stored charge phenomena doesn't occur, so therefore the parasitic capacitor which was we was mentioning during the PN junction, so that parasitic capacitance is absent in case of the Schottky diode, so therefore it has a very fast recovery time. Okay, so but the problem is as this it is a very thin depletion region or the space charge region, that peak inverse voltage is very less for the Schottky diode. So you can write down that the peak inverse voltage, so that comes under the disadvantage. So disadvantage is PIV. PIV is very less in the order of 100 volts only. Okay, but the advantage is advantage
Sir, your voice is again breaking.
cracking. What can I do?
Yes.
So I'm just stopping the share. I'm trying with a different connection. Okay, so as I mentioned that the problem of Schottky diode is very less peak inverse voltage. So therefore, sometimes we use a different material instead of this platinum or that is gallium arsenide or silicon carbide. So if you use the silicon carbide, then PIV can be up to 250 volts, or if we can use this that's the gallium arsenide, then it can be up to 400 volts. Okay, so these are the change in design we can make so that we can get more PIV in case of Schottky diode. But that is the major problem for Schottky diode, that it doesn't have a very high PIV. So now it has come. So let me share. Okay, now we can see that board. Can you see the board?
Yes, sir.
Okay, so you can use silicon carbide SiC to get the PIV up to 250 volt. Silicon carbide SiC can be used to get PIV 250 volts. Okay, but again the cost for this type of thing will be more. But one thing is very clear, that by using the Schottky diode we can get a less recovery time. If you need a very fast switching, then we can go for this Schottky diode. Okay. Now let me discuss the thing we were discussing in the last class, that is the Snava circuit. So the Snava circuit generally contains capacitor and a resistance in series to avoid the. Can you tell me why this resistance is used for in Snava circuit? Anybody?
To prevent RC oscillations.
To prevent LC
LC oscillation, RC.
LC.
Correct. LC oscillation. To prevent the LC oscillation, we use the resistance in series with the capacitance, isn't it? So that is the thing. So this is the Snava circuit. Now, what is the function? If we can function of this Snava circuit. What are the functions? The one function I have already mentioned, that it protects the high high reverse voltage, because if we see that how the voltages are formed here in the curve, then the voltage is formed like this. If I draw it like this, on state there is no voltage. Okay, because on state drop for the diode is very less. Now if there is some didt, so all these portions are giving some didt, so all this portion is giving the didt, so it will be high and it will go like this. So this is the plot of voltage. You can say this is the voltage. Okay, now this voltage depends on this didt, and the purpose of using this capacitor across this in parallel with this diode is to bypass the high didt through this capacitor, because capacitor doesn't change, doesn't allow the change in voltage. Okay, so that means if we discuss the functions of Snava circuits, the first is it protects the diode from high reverse voltage, negative voltage during reverse recovery. So that is one region that I've already explained in the last class. Now another reason is that, so every device, I think I have mentioned in the first class that every device had its own this Didt and dVdt rating. Okay, so we can write here also once more. Every device has its own dVdt rating, which is mentioned in the data sheet of that particular device. The dVdt up to which dVdt it can withstand, that is clearly mentioned in the database of any device. And if the dVdt is more than this value for that particular device, then there will be some damage of this device, because the insulation present in this device cannot withstand that. Okay, so what happens if there is some high change in voltage across this particular device? Now suddenly that device can damage. So let me draw this. Suppose this is the voltage across this device and this is the time. Okay, now if this is very high, very steep dVdt, very steep dVdt. Okay, so if the external voltage applied is changed very fast, then it will give rise to this dVdt, very high dVdt. Okay, and if this dVdt is more than the rated dVdt of this device, then the device can be damaged. Okay, so it's called the breakdown of the diode. Now, if we apply this Snava circuit, or this capacitor in series with the resistance uh, with this device, this particular device, then the resultant change in dVdt can be reduced like this. Okay, so that means this is with RC Snava. So this is the without Snava dVdt, and this is the with Snava dVdt. Okay, so that means by this Snava circuit also we can save the device from first switching. Okay, so though it is not a device phenomena, fast switching is a completely external phenomena from the supply that can come. But by using the Snava circuit, we can save the device from a very high dVdt. So that is the another function of the Snava circuit. So for that, in most of the power electronic device, we use a separate Snava circuit. Okay, so that is the thing related to the Snava circuit. Now come to the equivalent circuit of diode. I think you all know that what is that. Equivalent circuit. So before equivalent circuit, let me discuss the characteristics of diode. I think that is also know what is the characteristics, and generally we draw the IV characteristics in case of diode. As I mentioned in the last class that due to the space charge region, the resistance becomes more. The on-state resistance for the diode becomes more, but that you can say a disadvantage of this space charge region which is present in the power diode. But I will say that that is an advantage of power diode because that gives a more linear characteristics. So these characteristics becomes linear, and if we take the gradient of that, so that will give me the RD, which is called the inherent resistance of the diode. Okay, and if we extend the slope of this RD, the point at which it intercepts is called the threshold voltage VT. It is called the threshold voltage VT. Is that clear? So am I audible clearly? Because at my end it is showing that your connection is unstable. So therefore I'm asking you that whether I am clearly audible.
It was breaking.
So audible, but
Thanks, sir.
audio is distorted.
Okay, I don't know. I have tried with another connection. Okay, so you just try to understand because I'm also drawing that as much as possible. I'm drawing and writing the thing in the board. Okay. So if this is the case, if this is the RD and this is the threshold voltage, so what should be the equivalent circuit? Can you tell me that if we want to represent the diode?
Sir, can you explain the threshold voltage again?
Threshold voltage means if we extend the RD line, because once it goes exponentially, after that it becomes almost linear. Though though it is an exponential, but the portion we are observing is mostly linear. So if we linear means if we extrapolate this line, if we increase the line in this towards this x-axis, then it will intercept at a particular point, and that point of interception is called the threshold voltage VT. That means this is the threshold voltage VT, and it is only for a very small voltage, and 0.6 to 7 volt for silicon and zero point 0.4 to 0.5 volt for germanium. So this is VT, which is 0.6 to 7 volts for silicon and 0.4 to 0.5 volt for germanium. Okay, so RD is called the dynamic resistance. Dynamic resistance of diode. Okay. Now, if that is the case, if we have these two things, now if I want to represent the diode in form of an equivalent circuit, equivalent element, what kind of element in terms of linear elements rather, what kind of elements will be there in the equivalent part?
Sir, a resistance and a voltage source in opposite in reverse.
Okay, so correctly you have said that we should have some voltage source in opposite direction and in series with a resistance RD, isn't it? So this is the VT
Yes, sir.
and this is the RD. So that is the equivalent circuit of diode. Okay. Now here we have this voltage drop. IDR. Okay. Now we can also derive the power dissipated in the diode. So you know that power is nothing but the multiplication of voltage and current. And whenever we are writing this small p, the small p is basically the instantaneous power. So all these small letters are used to represent the instantaneous value. And this VD, so this is the total is VD. So VD is basically VT plus RD. So let me draw it here. So this total voltage is VD. Total voltage drop across the diode VD. So VD is what is VD? VD is VT plus IDRD into ID. So that is the instantaneous power. Now, if that is the instantaneous power, then what will be the average power? Because average power is having the unit of watt, or you can say the average power is analogous to the active power in case of sinusoidal assumption. So average power dissipated in the diode will be capital P, and that is the average of this value, that is the PD dt 0 to t. Okay, and we have 1 by t 0 to t. If we substitute that, so it will be Vt plus IDRD into ID already there into dt. Okay, again it has stuck. Okay, now here we have two terms. One is not function of time, another is function of time. So this is 1 by t 0 to t Vt dt plus 1 by t 0 to t I square Rd dt. Okay, so finally what we'll have this Vt.
Sir, it will be VT into ID dt.
Which one? Okay,
The
so one
first
more ID. Okay, one more ID will be there. So let me change this. So it will be ID. Correct. Thank you for this correction. So then we'll have, so Vt will come out from this derivative integration, and we have again Rd will come out. So this is your Vt. Now what is this value? What we can say about this? What we can say about this? Can you tell me?
Average value of current.
average value of current, correct? So that means we can write this is I average. And what about the second one? 1 by t into 0 to t id square dt. What is that?
So square of RMS
So this is the
means 1
RMS.
by t term to include whole.
Okay, so this is square of RMS into RD. So that is the final expression of average power dissipated in the diode, that is Vt plus I average plus I RMS square plus RD. Okay. So this is all about the power diode. Then we'll start the transistor, power transistor. So if we have
স্যার
any
আরডি যোগ হলো স্যার আরডি যোগ করতে
যোগ
থেকে ওগুলো তো ইয়ে ছিল গুণ ছিল তো
হ্যাঁ গুণ ছিল তো গুণই হবে। Thank you. Power transistor. So if you have any doubt regarding this, you can ask. I have completed the power diode, then I will start the power transistor today. So if we summarize the power diode, whatever we have discussed. So what we have discussed, we have discussed the formation of a power diode and what are the different what are the structures which is practically available as a power diode. What are the different layers in the power diode? We have seen that not only this p and n type substrates are there, you have p plus, so if, p plus, n minus and n plus substrates are present in power diodes. So let me go back to this. So only for a quick recap. Okay, so I don't have this in the slides. Anyway, but we have discussed in details what are the phenomena going on this normal diode as well as power diode and how the currents are conducted. Okay, and what are the different types of diode? That is, we have discussed general purpose diode and other different types of diodes we discussed. Then the reverse recovery phenomena we discussed, in which we have seen that the diode takes a definite time to come back to its original state. Now, due to this reverse recovery phenomena, there is a problem of high DIDT, and due to that consequence of damage, possible damage of the diode. So therefore, we use the Snava circuit to protect the diode. And now Snava circuit not only protect the diode, but also it protects the high DVDT which can come from the external device, external power supply. Now there are, depending on this, based on this recovery time, diode can also be classified into two types. One is soft recovery diode and hard recovery diode. Now soft recovery diode has very, compared to this hard recovery diode has less DIDT, so therefore it is preferable for normal applications. Okay, and the Snava circuit has a capacitance in series with a resistance. And we also discussed that what is the exact definition of TRR, reverse recovery time today, and the the minority carrier distribution during the switch off, how it changes with time during the switch off, that we discussed today. And one more thing we discussed, that all the PN junction diode can be thought of uh, constituted with the parasitic capacitance connected in parallel, and due to that it takes some time to switch on as well as switch off. So that means the storage charge phenomena occurs in case of PN junction diode, but that is not there in case of the Schottky diode. So Schottky diode is a majority carrier device, and it doesn't have any P substrate, only N substrate it has, and a thin metal plate. Now the Schottky diode can be used for very fast switching, but it has some problem of less PIV. But if we can use a different metal, then we can increase the PIV little bit. Now then we discuss the different function of Snava circuits and the equivalent circuits. So equivalent circuit is very simple. It has a threshold voltage in series with a dynamic resistance RD. And then what is the power dissipation in the diode? Because during the first switching, the power also should be considered. Accordingly, the heat sink we have to design. So these are all which we have discussed regarding the power diode. So if you have any doubt, you can ask me.
Minority carrier distribution.
Minority carrier distribution I have drawn today, but I don't have that time, or you don't have uh, that the scope of you don't have that scope of that details in your syllabus. So this is the minority carrier distribution that I have drawn today, and how it changes with time in the reverse in the switch off transient. So this is the initial one when the diode was carrying the current. Now, if we switch off switch off the device, then the minority carrier distribution changes like this, like this. At the end, there is almost zero concentration of minority carrier in the drift region, and there is only some concentration around the this junctions P plus N minus and N minus N plus junctions. So this is the minority carrier distribution. During the off transient, this is the minority carrier distribution. Is it okay? Ankit?
Yes, sir. Yes, sir.
Okay, so you can say that this is the NP and this is the PN, because this is the piece, this is the P in N. So this is the concentration of P in the N substrate with is a function of X, as is the X, and here that both the concentrations are same. So this is called the minority carrier distribution, and I have drawn only for the switch of transient. Okay. Any other query? Any more doubt? On power diode? Okay, so next we'll start the power transistor, which is the similar to the signal transistor we have studied. Huh?
Sir, your voice is breaking.
Again, the voice is breaking. I don't know how I can avoid this. Just a minute. Am I audible?
Yes, sir, yes.
Still the voice is breaking or clear? Is my voice breaking or it is clear?
No, sir.
Clear, sir.
I don't know what is yes and what is no, but still I cannot. I don't. I know that I cannot continue with this because here also it is showing that your internet connection is unstable. Anyway, but I should start the power transistor today. Otherwise, it will be too late. So as we have you have learned something in your electronics class that signal transistor. So here also in power electronics you have power transistor which is used for the power controllers. There are different types of power transistors. The difference is as we have already mentioned in case of power diode and signal diode, the difference in the power handling capability. So power transistors has the power transistors have more power handling capability. So that means the voltage and current is more in case of power transistors. Okay, so there are different types of power transistors. You know that one is the bipolar junction transistor. So bipolar junction transistor. Bipolar junction transistor, or it is called the BJT. Another one is the metal oxide semiconductor. Metal oxide semiconductor. Field effect transistor. Effect transistor, or it is called the MOSFET. So I will discuss one by one all these things. Next, we have insulated gate bipolar junction transistor. Insulated gate bipolar junction transistor, or it is called IGBT. And so this third one and the fourth one is static induction transistor. So these are the most common transistor which are used in power electronics applications. Okay, now we'll start with the bipolar junction transistor. Anything in the chat? So I know that my voice is breaking, so therefore I am not discussing many things. So only I am writing some names. I think it will be. You can see, can you see the board?
Yes, sir.
So that will be
Yes,
enough,
sir.
I think, because I know that today I cannot continue with this. So therefore I am not discussing too much. So only I'm writing something, only I'm mentioning the name, and I will discuss all this in the next class. Not only all this, I will start the bipolar junction transistor in the next class, and it will take 2 to 3 class. Then we will start the metal oxide MOSFET and IGBT. So anyway, I should stop here because internet is giving lots of trouble today. So I should stop here. Now, the thing I want to tell you that the participation is very poor for your class, particularly your class, because I am taking the class for final year, I am taking the class for second year. Both the cases, the participation is very good. For final year, it is 100%, and for the second year, it is almost 80 to 90%. But for you, it is less than 30%. I don't know why. Not 30%, less than 50%. What is the reason? Because all this class now becomes official class. So I am taking the attendance every day. So you should participate. You should attend in more numbers. Okay. And from the next class, what you will do when you will enter to this room, Zoom meeting room, you just rename yourself with the roll number first, then underscore your name. Okay. And then it will be
Full roll number.
the last 3 digit of your roll number first, underscore your name. It will be easier for me to take the attendance. Okay, so maintain this convention for renaming yourself from the next class.
স্যার এটা কোথায় গিয়ে করতে হবে?
You go to the participant list. Do you have the participant list? At the bottom, you have a bar. There you see the participants 25 is written. You click on that, then you will get the participant list. Now on the participant list, you search your own name, and if you
ও আচ্ছা স্যার পেয়েছি পেয়েছি
mouse over there, then you will get
পেয়েছি।
the more option. In the more option, you will get the rename
ওই রিনেম
rename option.
ও রিনেম অপশন রয়েছে, হ্যাঁ স্যার পেয়েছি, দেখতে পেয়েছি।
So
ঠিক
rename
আছে ঠিক
option
আছে।
is there. So you do that from the next class. So I am taking the attendance for today by taking the screenshots. From the next class, I will take the attendance in the sheet. So you just wait some time. I take the attendance in screenshot. But the attendance is very poor for your class. That is the thing to be worried. not in my class, as I heard that not in my class. In general, your attendance is very poor. Is it so? Now, as there is no physical class test or assignments, so I will give you some assignments, and uh, at the end, your attendance will have some reflection on your marks. So you just remember that, and you just let your other friends know that this attendance has will have some reflection on your marks. Okay.